Oh, hi, Tina. Your question 39 under 8.2 is a very complicated question. So instead of typing up all this information online, maybe I can just use this screencast and try to help you go through that. Okay. Now, so what happened is when you look at a question, which is here. So the solar energy represented by S over 4, which is about 350 watts per meter square. That is the intensity. So that's the solar energy coming in, and some of them will pass through, some of them will be reflected back into space, and by definition, that is called the albedo, which is defined by the sigma or the alpha symbol right here. So solar energy shines on the atmosphere. Some of them will be reflected back. Most of it will be passing through. And what happened is when the Earth's surface receives the energy from this part, I'm circling from this part, it will radiate back into the atmosphere because we assume the Earth, the surface, is a black body, as said in the question. So by definition, black body means whatever radiation received, it will give it back in return, 100%. So this is the amount of energy received on the surface, and I1 is the amount of energy returned back to the atmosphere. But because they was in the atmosphere, some of the energy also reflect back because of the albedo back to the surface. So I1 is the amount of energy radiating back to the atmosphere, this is how much energy reflected back to the surface. So the atmosphere will be absorbing the rest of the energy, which is 1 minus alpha times I1. That will be scattered into 3 radiations in this model. So that energy received by the atmosphere, which is 1 minus alpha, brackets, 1 minus alpha, times I1, which is this part, it will scatter into 3 radiations, I3, I2, and I2. This I2 goes to outer space, this I2 go back to the surface. So part A, it says intensity radiated by the Earth is I1, which is this one. Okay, intensity radiated by the atmosphere is I2, right? These two, and so forth. By examining the energy balance of the atmosphere, show that I1, I2, I3 just like that. Now, so let's go back to the solution. And from the solution, you can see that it looks really complicated, but it is not quite, right? You probably be able to understand. So I1 is the radiation by the surface, and the fraction of it escape. And that's what described in the question, such that I3 equals to T times I1. So I3 equals to T times I1. And then intensity of the radiation entering the surface will be this much. Now let's look at this representation. This is 1 minus alpha S over 4 plus alpha I1 plus I2. So you may wonder, where is it from? This part is 1 minus alpha S over 4 because alpha has reflected back. This is 1 minus alpha passing through. What about this one? This is a reflection back to the atmosphere from the Earth's radiation. So alpha I1 and I2. This is pointing towards the surface. So when you add this one, and this one together, you will get this. Okay? And because Earth is a black body, whatever radiation received equals to the whatever radiation coming out. All right, so that's why this must equal to the intensity radiation leaving the surface. Okay, so that means I1, which is just this line, this is the radiation leaving the surface. This line must be the same as this plus this plus this. And then after all, it is basically a math problem. Okay, and now, my free version of this Screencastify thing can only record, I don't know, 3 minutes, 5 minutes video. I only have 10 seconds left. Maybe I can record another video. Okay, so let me just stop for now.